Now we're going to continue looking at practice problems related to solving differential equations. So first we're going to think about what this means numerically. So we're not going to find the specific function that is the solution to the differential equation, but we'll think about the value of the solution at different x values, or t values in this case. So here we have the differential equation dy dt, that is, y is a function of t, and its derivative is equal to the square root of y. We're going to try to fill in the table of values below. We're going to assume that this rate of growth, this derivative, is approximately constant over each unit time interval. I'll explain what that means and what else we could do with that. There's going to be a homework problem that doesn't assume that, and we'll see what that means here. So looking at this function, we have that when t is equal to 0, our solution has a value of 144. So again, our solution is a function of t, and we're saying when that value is 0, we have a value of 144. We know that the derivative at that point is going to be the square root of y. That's going to be the square root of the function value. 144 is going to be 12. So the derivative is how much it's changing per unit value. So we're saying as we go from t equals 0 to t equals 1, we are going to be adding 12 to our function value, which means that we can approximate the function value at 1 to be 156. And then the derivative equal 12 is obsolete at this point. We can say that it's going to be about 12. It's going to be constant over each unit time interval, which means that we're going to assume that it's 12 for the entire t interval 0 to 1. But at that point, then we need to redo our derivative. So at y prime of 1, we're going to say this is equal to the square root of 156. We'll just leave that as square root of 156. And that is going to be our derivative. We'll say also square root of 156 is about 12.5. So this is saying on the second interval, we are going to add 12.5 to get our next value. So our next function value we're going to look at is 168.5. And we're going to rinse and repeat a few more times. So the derivative value at 2, we're going to say these are all approximations, is going to be about the square root of 168.5. This square root business comes from our derivative. And this is going to be about 13. 12.98, but we'll say about 13. So to go to this next value, we're adding 13, and that's going to give us a total of 181.5. And we're going to rinse and repeat one more time. The derivative value at 3 is going to be about the square root of 181.5, which is about 13.5. 13.47, but we'll call it 13.5. So to get to our next value here, we're adding 13.5, and that'll give us a 195. So at each point in time, we are taking the function, the derivative given by square root of y, and we're using that to find the next value. I may have misspoken. This is how we're going to deal with it on the homework as well, the problem. I said it was different. but it is going to be the exact same sort of idea. This constant over each unit time interval is saying from 0 to 1, the derivative is not 12 at every point in there. But just for the ease of this problem, we're going to assume that it's constant over that entire time interval. It makes the calculations much easier. All right, so that's looking at something numerically. For the rest of these videos, we'll think about it graphically and just as the functions we've been doing before. So this one says, determine if the following are solutions to the differential equation y double prime plus 2y prime equals 15. Note that this y double prime is the second derivative. Again, this is an equation with a derivative in it. In fact, there are two different derivatives here, but it's still a differential equation. In this class, we are mostly going to be focused on equations with just the first derivative, but we will venture into this a couple times. So we have four things we're going to check are solutions or not. The first is y equals e to the 3x. So to plug this in, we're going to need to find the derivative and the second derivative of this function. The derivative of e to the 3x is 3e to the 3x. And the second derivative is going to be 9e to the 3x. So plugging these functions in, we have the second derivative plus 2 times the first derivative, 3e to the 3x, is going to be equal to, and actually there's a typo here, so sorry, this should say 15y on the other side. Otherwise, this doesn't really work at all. So 15y on the other side, that's our differential equation. So this is going to be 15 times e to the 3x. So let's see if this works out. On the other side, we have 9e to the 3x plus 6e to the 3x. That is 15e to the 3x. And that's what we wanted to get. So our first one, we have a resounding yes. This is a solution to the differential equation. Okay, again, our differential equation should be 15y, not just 15. All right, let's do it 3 more times. So y equals e to the 2x. The derivative is 2e to the 2x. The second derivative is 4e to the 2x. Plugging this in, we have 4e to the 2x plus 2 times 2e to the 2x. And this should be equal to 15 times the original function, e to the 2x. So again, this is our second derivative, this is our derivative, this is our original function y. So this is going to say that 4e to the 2x plus 4e to the 2x, that's 8e to the 2x, and that's not the same thing as 15e to the 2x, so this is a no. That is not a solution to the differential equation. All right, next one, y equals x, a different kind of function here. Let's see if this one works. The derivative is 1. The second derivative is 0. So this is saying 0 plus 2 times 1 is equal to 15 times x. 2 is not the same thing as 15x. So this is a no. And it's worth thinking, is there another solution to this differential equation that looks, maybe you have e to the 3x plus a constant or something that might work. Maybe it's times a constant. Is there anything else that might work? And we'll see in this last one that maybe something else will. So e to the negative 5x, the derivative of that is negative 5e to the negative 5x. The second derivative is positive 25e to the negative 5x. Plugging this in, we have 25e to the negative 5x plus 2 times negative 5e to the negative 5x is equal to 15 e to the negative 5x. Again, y double prime, y prime, and y. And here we have 25 e to the negative 5x minus 10 e to the negative 5x. That is 15 e to the negative 5x, which is what we wanted. So this is a solution. So if you were to take a differential equations class, this would be the second part of the course. You would learn how to solve differential equations that look like this, and you would find that actually a general solution to this equation, this is not something that we need to know, would actually look like y is equal to some constant c e to the 3x plus another constant, we'll call it c1 and c2, e to the negative 5x. So any linear combination of e to the 3x and e to the negative 5x would be a solution. We're not going to need to know how to do that in this course, but just showing you that's what it is. All right, next example. Let's think about the graph of the solution of the differential equation. So the first one is the differential equation we looked at before. This is y prime equals y. And we're going to start with the graph on this one. We know that this is going to be something like e to the x. We showed this on the first video, why that's the case. So our solution should be something like e to the x. We'll say this is a particular solution. Now let's just think about graphically, does this work? So we're saying that for any y value, so let's even pick, y equals 1. So at y equals 1, the derivative of the function should be equal to 1. And we think about the tangent line here, the slope of that tangent line is equal to 1. We think about maybe a point like 5, the slope at that point is much steeper, and we're saying it actually has to be equal to 5. We think about a point down here, maybe like 1/2. And we get the same thing. And the graph that actually comes out is this e to the x. It's a special function that has this property. All right, in the next one, let's actually try to build the graph and show what the general solution might look like. So here we're going to look at different x values. Let's look at 0, 1, 2, -1, and -2. And we're saying at these points, the derivative should be equal to the x value. So at 0, the derivative should be equal to 0. So the slope is equal to 0 here. At 1, the derivative should be equal to 1. And I'm kind of putting this in a nice way to sort of show what's going to happen. At 2, the tangent line is going to be like a slope equal to 2. At -1, the slope is equal to -1. And finally, at -2, we have slope equal to -2. And if you would kind of connect the dots here, we would get something that looks like this. It's a rough sketch, but it's going to be something that looks like a parabola. And we do know that if we take the antiderivative of x, we get a 1/2 x squared plus c. And if you start with the function, you can kind of see how that would work, that the slopes start really negative, they go to 0 and they get positive. We are not going to have to play with individual graphs like we did right here, but again, it's to show the relationship between the function and the derivative given the graph as we looked at it numerically in the first example. So again, if we started with the graph here of a parabola, we can see that the slopes start really negative, they become 0, and then they get positive, just like the x values do. All right, last example here. Let's look at an initial value problem. So first, let's find the general solution to the differential equation y prime equals cosine. So we know that we can take the antiderivative of cosine with respect to t. Why are we doing t? Because that is our value here we're looking at. This is dy dt, our variable. The antiderivative of cosine is going to be a positive sine. And we need our constant of integration plus c. This is our general solution. To find a particular solution, we are going to use an initial value. This is our initial value. This pi corresponds to our x value, and the 2 corresponds to our y value. Again, this is like saying f of pi is equal to 2. So plugging this into our condition, we have that 2, our y value, is equal to sine of pi, our t value, I should say, not x value, our t value, plus c. Now sine of pi we know is equal to 0. So this is going to be 2 equals 0 plus c. So c is equal to 2. So our particular solution is sine of t plus 2. Our general solution, and then a particular solution where we find the c value that corresponds to the initial value condition y of pi equals 2.